topic close to my heart, never-ending learning. It's actually a research direction that I'm engaged in, and so I'd like to talk about that today. And as you'll see, it touches on several of the topics that we've covered during the course. And then Wednesday, we're going to talk about neural networks and deep learning. So that's the plan for this week. So never-ending learning. Here's the idea. Actually, by the way, these are all people involved in the project, including people like Abu here, and many other interesting people. Professor William Cohen, who teaches the big data machine learning course, which you might want to take, or some of you are taking this semester, is involved. Professor Stefan Hruška, who is a professor in Brazil, but comes and hangs out with us every January because he loves Pittsburgh Winters so much, and a number of other people involved in the project. And here's the idea. The idea is, think about what we've talked about in this class on machine learning. Mostly we've talked about, well, the primary topic we've talked about is really function approximation. Right? Given training examples of input and output of some function, we want an algorithm that can guess what that function is in a way that accurately extrapolates to new examples that we didn't train it on. And we talked about logistic regression, we'll talk about neural nets, we talked about linear regression, we talked about decision trees, support vector machines, lots of ways of doing this. Now, here was the observation that got me started down this path. I was talking with my mother and explaining to her that I work in machine learning. And she said, fine. She's a very smart person, but she's not a computer scientist. And so she asked me, what do you do? And so I started telling her about these function approximation problems. And she said to me, I watched you grow up. That's not learning. So she's right, as mothers often are. And so here's the thesis that underlies this research. We'll never really understand learning in computers or in people until we can build machines that, like you and I, learn many different things over a long period of time with very diverse experience. For example, we learn to crawl, then we learn to walk, then we learn to ride a bicycle. In parallel with that, we learn to count, then we learn to add, then we learn algebra. Then we learn graphical models. In parallel with that, we learn how to pick up stuff, and later physics. And we get synergy between all these things in very interesting ways, right? That calculus course you were taking helped you learn physics and vice versa. So we're different kind of learning machine than the kind we primarily talk about when we talk about a program to estimate one function given input and output examples of that function. And so, and furthermore, we do become better learners over time. We don't just become better estimators of the output of the function given the input. We also become suddenly capable of learning material that years ago we weren't even in a position to learn. So the question, the brain teaser, the theme of this research question is, what would it take to build a computer program that, like us, learns for years and gets better in these various ways? So we don't know the answer to this question. But I think it's an important question for the field. If you think about just the evolution of the field of machine learning from decade to decade, and it's only about, well, let's see, the earliest interesting work I know is the work on perceptrons and the work that Art Samuels did building a checkers program that learned to play checkers better over time. That was late 50s. So the field is about 55 years old now. And if you go forward another 20 years, I think the field will grow and hopefully grow in a way that we can take on these kind of problems. So So that's my motivation. So what are we doing about this? Well, we don't know the answer, but we thought we would pick a case study and try to build a computer program that learns for years. And the task we chose for this case study was to learn to read the web. So reading the web, really reading, not just you give me a search key and I return the page, but really read and understand as you and I would. Computers can't do that today. And so we thought it was a challenging enough problem to warrant years of learning. And so here's the way we set up the problem. First of all, the task for the program is to run 24 hours a day forever. And then each day do two things. Extract more facts from the web, structured facts from that unstructured text that's out there, to populate a growing knowledge base, which is currently about 90 million beliefs. We'll look at that. And number two, each day it also, this is just as important, should learn to read better than it could yesterday. Meaning it should, if we send it back to this, if it has learned to do better today than yesterday, the evidence for that would be that we could send it back to the same text it looked at yesterday, and it should be able to extract more facts more accurately today if it had learned to read better. Okay, so that's the way we set up the task. Make sense? And then what's the input to the program? Well, there's the input. We define an initial ontology, which means categories, a set of category predicates and relation predicates we want the system to learn about. For example, we told it we wanted to learn about people and athletes and sports teams and which athlete plays on which sport team and so forth. We give it for each of those predicates a dozen labeled examples. So if we say we're interested in sports teams, then we give it a dozen noun phrases that refer to sports teams. Pittsburgh Pirates, New York Yankees, Pittsburgh Steelers, that's it. And then the web, and occasional interaction with human trainers. And I'll say more about that. Okay, so there's the task. So as you can see, we've kind of set this up as a challenge to ourselves to try to build a computer program that can keep getting better over time. All right, so where are we today? Well, the system, we call it Nell, Never-Ending Language Learner, has been running since January 2010, so we just had its 5th birthday, big party. And it currently has a knowledge base that it has extracted with about 90 million beliefs and probabilities, confidences associated with each of those, plus for each of those, a pointer back to the source, the text from which it obtained that belief. It is learning to read. It is a better reader today than it was a year ago, and it was better than the year before. It's also learning to reason, to do inference over the knowledge base that it has built. And it's learning to extend the ontology by making up new predicates, new categories and relations that we didn't give it, but which this part of its learning tasks is to expand its representation. Yes?
So I think part of the way we learn is that we have this like meta-analysis of our own learning, right? Like is our approach the correct way to learn this subject matter? Does Nell have something like that?
Something like, you say we have a meta-analysis. What does that mean?
Like maybe my approach to learning about this thing isn't the most effective. I'm going to try another method.
Yeah, that's good. And yeah, part of what makes us good learners is we can kind of go meta, self-reflect, strategize that this isn't working, maybe I should talk to the TA. Nell is not very good at that at the moment. So I think that's one of the self-reflection and more targeted use of time is one of the areas where Nell is pretty impoverished, actually. But that's a great area for actually for the next stage for Nell. Okay, so let me show you a little bit more detail what I mean by this. When I say Nell has a knowledge base with 100 million beliefs, here's what I mean. Each of these red arrows represents some belief triple, like the Maple Leafs are in the league NHL. And one of their members is a person named Sue Din who plays in the NHL. So do the Red Wings, whose hometown is Detroit, which has a company called GM, which competes with Toyota. So each of those triples, each of those red arrows represents some belief triple. And not shown here is the fact that underneath each of those is a confidence score and a pointer back to where it came from. Also not shown here, in the spirit of full disclosure, are other incorrect beliefs that Nell has about these items. So when I put together this slide, I chose just things which happen to also be true. And there are plenty of things Nell believes at different levels of confidence which are in fact not true. And part of our measure of whether it's learning and getting better is, can it in fact over time improve the quality, the accuracy of the things it believes. Okay, so in fact it is getting better. So here's a plot. You can count a couple of different ways how Nell is changing. One is you can plot over time, that's the horizontal axis, just the number of beliefs that Nell has. And you can see it's growing both in terms of the total number of beliefs it has and the number of high confidence beliefs it has. Nell treats those kind of differently. It uses the high confidence ones to guide its subsequent learning more than it uses the low confidence ones. So that's one way of looking at it. Another is to look at how accurate is it at for each of the predicates in its knowledge base. So for example, if it's supposed to find noun phrases that refer to athletes or to beverages, which are two of its tasks, then what's the precision of how accurate is it if we, for example, take the top 10 noun phrases that it believes to belong to the category outside the training examples, new ones that it has brought in. And you can see over time, it's got a little bit better by that measure, more significantly better by mean average precision, which is just a measure that out of information retrieval that takes into account accuracy at the top, in this case, top 1,000 beliefs that it has per category. So it's getting better somewhat in both of these regards. You can also ask how much human feedback is coming into the system. If you go to Nell's website, you'll see that you can browse its knowledge base, and there's a little thumbs up, thumbs down icon where you can give it feedback. And people do, please do. But you can see over time the amount of feedback that it has received from humans, and it has averaged out to 2.4 feedbacks per predicate per month. So it's very lightweight human supervision, but there is some in there. So those are the statistics on the system. But let's take a look at Nell. So here's a typical kind of sample of things that it believes. If you go to the Nell homepage, you'll get a random sample of recently read beliefs, and this is just a screenshot from there. Jerry Patton is a chef. Flavones is a video game. Smith S. Rose bellied lizard is a reptile. Gray flycatcher is a bird. Basalt plains can be part of a landscape. Louisiana is located in the US. Kansas City Chiefs won Super Bowl, etc. Miller has been charged with contempt. It has a category called criminals. We'll probably get sued eventually. But let me drill down by browsing. Let's look at what Nell believes about one of these things, like you could take tea as a nice example. So among Nell's learning tasks are problems of the form, for every noun phrase that you can find on the web, classify it according to what type of item it is. So for example, Nell believes gray flycatcher is a noun phrase that refers to a bird, and basalt plains is a noun phrase that refers to part of a landscape, for example. So let's just drill down and look at, for example, the noun phrase tea, and we can use this to kind of illustrate. Is that big enough font in the back? Shall I blow it up? Better? Okay, so over here on this side, you see actually it's the different categories in its ontology. You can see, for example, it has categories from music album to fish to crime or charge to film festival to colors or days of week, political bills, economic sectors, etc. But tea is a noun, just a noun phrase that it found. And what does it believe about tea? Well, one thing it believes is that the noun phrase tea can refer to an agricultural product. Another thing it believes is that it refers to a food, that it refers to a beverage, and so forth. So, and for each of these, it has some confidence. It's very confident that tea can refer to a beverage. And if you ask why, here you see its justifications. It actually has multiple. But for example, one type of justification has to do with the phrases that it found around the noun phrase tea. And it found tea occurs in the context of large cup of tea, or afternoon cup of tea, or drinking cups of tea, or fire, boiling tea, or way I drink tea, or tea is a traditional Chinese tea, and so forth. So these are all phrases on the web in which Nell has found the noun phrase tea, and each of these gives it a little bit of probabilistic evidence that tea could be a noun phrase that refers to a beverage, and taken together, it has very strong belief that tea in fact is a beverage. Another way that it justifies it is by looking at the actual string of letters. And because T ends with the two letters EA, it believes there's a positive weight, 4.7, that it could be a beverage. For tea, I think this is kind of maybe self-referential. Maybe once it believed tea was a beverage, then it started noticing that tea itself ends with EA, but maybe there are other beverages that end with EA. It also has a number of web pages where it found tea. Let's pick one of these and see if it's still available. No data received. Okay. It's pointing out to URLs, some of which are dead, because I can see it did this back in September 2000. Okay, well, there's a website called the Boulder Danube Tea House, which somewhere on here, maybe in a drop-down menu, mentions tea. And apparently it had found other beverages on this. It looks for various regularities on web pages, and there was something about this web page that made it think it was affiliated with beverages. Hence, it believed now that tea is also. So here you get some idea of when we say that it's reading the web or learning to read the web, it's reading in a sense that's very different from you and I. Right? You and I would take a sentence and understand it in depth. What Nell is doing here is looking at many, many pages on the web. In fact, it has downloaded roughly 1 billion pages. And Google has given us permission for Nell to call its secret software API search engine 100,000 times a day. So Nell is collecting new pages every day, and it has a cache of pages. So its notion of reading, at least for classifying noun phrases, is to aggregate shallow analysis from many different places on the web and to combine those pieces of evidence into a final belief. If you ask me, why did it decide these are the right contexts for deciding that a noun phrase is a beverage, the answer is that's what it's been learning for the last 5 years. So we didn't give it any of these. We just gave it, remember, for each predicate, a dozen examples. So for beverage, we gave it a dozen examples. Maybe Coca-Cola, water, orange juice, whatever. And from those, it used a semi-supervised learning algorithm, which we'll talk about in a minute, to, over time, learn that these were phrases it should use as indicators that a noun phrase in these contexts would be a beverage. Okay. So before we leave this, I want to show you a couple other things. What else does it believe about tea? It believes it's a visualizable thing. And then it believes tea participates in some relations as well. So it believes tea is an agricultural product that came from the country Australia. And again, that's partly justified by phrases it found, like tea tree indigenous to Australia, for example. It believes that tea also comes from China. It has a number of reasons for that, including these various particular web pages and phrases. It believes tea comes from Hong Kong, Japan, Republic of India, Singapore, UK, Vietnam. You get it. It also believes tea is an agricultural product that contains some chemicals, like antioxidants, right? Like tea and red wine, can't even read that one. Tea contain the highest amount of antioxidants, for example. Tea contains catechins, compounds, fluoride, sugar, caffeine, properties, substances. It believes tea is an agricultural product growing in different provinces like Sikkim, West Bengal. It believes it's grown in certain types of landscapes, like tea is grown in foothills and mountains. It believes tea is made from other beverages, like juices. That seems odd to me. I might call that an error in its beliefs. It believes that this is it's kind of a funny name for a relation, but inverse of agricultural product, including agricultural product. That's Nell's clever way of saying that it believes that tea belongs to a larger category called crops and products. And it believes that caterpillars like to eat tea, that tea is served with baked goods like biscuits, breads, cake. You get the idea. Okay, so it actually has a rather complete set of beliefs about tea at this point, now that it's 5 years old, that it has accreted over time by learning different reading classifiers, I guess I'll call them, associated with different relations, different categories. And so you see this is kind of the current effect of this. And one reason I wanted to show you tea is it turns out that all of the relations that tea is involved in here, like inverse of baked goods served with beverages, are relations that we did not give Nell in the original ontology, but are relations that it made up along the way because it decided, with an algorithm we'll talk about in a minute, that this would be a good relation to relate certain known beverages to certain known baked goods. Yes?
I have two questions. One is, what does Nell do with slang? I mean, is it able to actually pick up slang? And second one is, how does it, I mean, does it really take into account data recency? Because 10 years from now, those beliefs may completely change.
Yeah, right. So slang, Nell doesn't know that slang exists, but it just knows that these text tokens out on the web exist. So it will treat slang exactly the same as it treats everything else. When we look at the learning algorithms, you'll see that, in fact, you can already see a hint of it, that because much of Nell's beliefs are based on aggregating evidence from many sources, if there's a peculiar use of slang that's infrequent, it will basically not be influenced by it. Most of his beliefs are really influenced by many different independent statements that are out on the web.
So does it try to stay away from social networks where slang would be more?
We don't stay away from anything on purpose. We just use a collection of web pages that was collected to be representative, plus the Google provided API for additional search queries every day. So don't really try to stay away from anything. Your second comment or question was interesting about recency. You know, some things that used to be true, like Bush is president, are no longer true. And Nell has a serious problem with that. In fact, dealing with time is in the top 5 problems that Nell is currently struggling with. It has a very inept way of dealing with time at the moment. So it actually believes that Bush is president, and it believes that Obama is president, and it believes you can only have one president, yet it's just got overwhelming evidence that both of these guys are president. So it doesn't, we have some research going on to try to deal with time, but Nell certainly is nowhere near having conquered that problem. Okay, so let's, you're welcome to browse the knowledge base. This is just the public knowledge base of Nell. As I promised, if you go to it, you'll see a random sample of recently extracted beliefs. So on April 12th, it extracted that Gaelic football is a hobby. Saks Fifth Avenue is a retail store. O'Connell Center is a tourist attraction. Nokia is a product. Online Poker Texas is a board game. I don't think so. Heat participated in the event games. That's true, there is a team called the Heat. Casey graduated from State University. That's probably true, but a little abstract. Latin is a language used in Northwestern University. I haven't been there, can't verify that. Quebec is located, so you get the idea. And then over here, if you don't like any of those, you can give it feedback. So you're welcome to, and invited to, browse at your leisure. Okay, so, and recently, Stefan Hruška, our Brazilian visiting professor, spawned a Portuguese version of Nell, which is trying to do the same thing using Portuguese language. But okay, for our purposes here, we want to actually look at the machine learning algorithms. So there's an overview of what Nell is trying to do. Now the brain teaser is, given what we know in this class, how would you architect such a system? What would you do? So today I want to tell you about what I think are the 4 best ideas in Nell, and in the discussion bring out some of the shortcomings, like inability to deal with time is really a big shortcoming. But there are 4 good ideas that I would recommend using for any never-ending learning system that we want to build. And so I want to take you through those. And the first one comes from the question of, okay, we just saw, for example, Nell believes the noun phrase tea is a beverage. What kind of semi-supervised learning algorithm should Nell use, does Nell use, to learn to classify arbitrary noun phrases into the hundreds of categories that it knows about? And so, for example, suppose I tell you, here are 4 noun phrases. These are my labeled examples I'm giving you. or your algorithm. And I want you to give me a semi-supervised, meaning it will use these labeled examples plus all the noun phrases you can find on the web as unlabeled examples of noun phrases. But these 4, I'm telling you, belong to the category I have in mind. Okay. So what could you do? You could probably think of a lot of things. But the first thing we thought about was, well, let's take these noun phrases. We'll search the web for instances of those noun phrases. We'll find contexts in which they occur. Like we might find mayor of Montpellier and live in Pittsburgh. And so then we can take these contexts as indicators of what kind of noun phrase here in argument 1 could be additional members of this category. And so we tried that, and you find things like mayor of San Francisco, live in Berlin, live in denial, and Nell did find this. Okay, so now we have 7 purported members of this category. We could iterate this process and go look for more context. And again, we might find Berlin is home of, and traits such as denial, and then we can just keep going. Okay, so this is the first thing we tried. It's not crazy, but as this example illustrates, it's also not the kind of algorithm you want to let run for 5 years. Because what will happen is basically a little bit of error will pollute the pool of purported examples, and then we won't really get very far after a year. So, but there's a kind of grain of good idea in here. And the problem, so at first we were thinking, oh, there must be a better algorithm. But I no longer think of it that way. I actually think that if this is the only thing I give you, that I have in mind some mystery category, and here are 4 members of the category, that's such a hard problem. What I have in mind, you have no idea. And to criticize this algorithm for giving the wrong answer is even crazy, because maybe what I had in mind was cities in the northern hemisphere, or cities in the northern hemisphere unioned with personality traits. Or maybe I had cities. I could have had any 3 of those in mind and given you this sample of valid positive examples of it. So there's a sense in which the real problem here is that the problem itself is under-constrained. It's under-specified. Right? There's no strict sense in which this is a wrong answer if all I say is there's some category that contains these 4, find other members. Unless I make some other assumptions. So good idea number 1 in Nell, of these 4 ideas, was to get out of the whole game of trying to learn a single function at a time, and instead force Nell to learn what turns out to be thousands of functions simultaneously in a very coupled way. So it turned out to be too hard to learn a single function that the input was a noun phrase and the output was a Boolean yes or no, telling whether that noun phrase belonged to a particular category like person. And it turns out to be a much easier semi-supervised problem to force your system to learn all these different, each of these black arrows represents a different Boolean function Nell is learning now. And even though this looks more complicated than that, this is also a much more constrained, better framed learning problem than the very barren, unconstrained problem that says I have a mystery category in mind and guess what it is. And the reason this is easier is because here we have not only these black arrows, but these green and red lines in this diagram indicate logical constraints that hold among the labels being assigned by these different functions. So let me push down on that and let's look in detail at what the algorithm is. So this idea of forcing the system to learn multiple functions at once, actually we identified 3 different types of coupling the training of multiple functions. One of them is what you heard about last week, co-training. So how does co-training show up in Nell? Very obviously. So suppose we want to train a function that, given an arbitrary noun phrase, has to predict whether that noun phrase, classify whether that noun phrase refers to a person, yes or no. Then one way we can represent the noun phrase is, as we saw, how frequently it occurs in different contexts. So you could think of this red representation of the noun phrase as being a feature vector where each feature is some context, and the value of that feature is just how frequently does the noun phrase in question occur in these different contexts. Okay, and then we could learn a function, let's say logistic regression, just to take one, that learns some parameters about how to weight each of these features to predict yes or no, is any given noun phrase a person. And when we train that logistic regression function, we would try to minimize our usual objective function, which is the sum over the labeled examples that we're given of the difference between the known label and what our function f1 predicts as labeled. Basically, we try to minimize some measure of the number of errors we make on the labeled data. Okay, so that would be standard supervised learning of a single function. But in Nell, we have several views. We also could represent alternatively the noun phrase just by its morphology, just by the letter string itself. Right? So if I have a noun phrase like Oblinsky, I could represent it by feature vector, like is it capitalized? Does it end with ski? Does it contain the 5 characters UNIV period? And these would be clues about whether it's a person or not also. And they're disjoint from these. They're nearly independent of these given the label, which is the property that you want for co-training. And so here, if we force the system to learn both of these functions, for any given noun phrase, we represent it both as the pink vector in terms of these context features, and we'll take Oblinsky and see how often it occurs in these things. We will also take Oblinsky and simultaneously give it a blue feature coding, and then we'll force these 2 functions to learn what? Well, for co-training, we want it to learn, even if Oblinsky is an unlabeled example, and we don't know whether we want it doesn't know whether Oblinsky is a person or not. At least in co-training, we want the learning of the parameters of F2 and F1 to result in F1 and F2 agreeing on the label. Surely they can't both be right unless they at least agree. And so we modify the objective function. Just as before, we want, with the labeled data, we want to make sure that both F1 and F2 minimize the number of mislabelings they assign given the noun phrases for which we know the value of the person variable, 1 or 0. But now we get to add this beautiful third term, which is for every unlabeled noun phrase, and there are tens of millions of them that Nell is using. We don't know whether it's positive or negative, but we know that if F1 and F2 are correct, they at least should agree. So we try to minimize the difference between what they predict. Okay, so this is just co-training. But now you can see how valuable that is if you're in a setting like Nell is, where you have a dozen labeled examples for each category you're trying to learn, and 30 million unlabeled noun phrases. This term in the objective that you're trying to optimize as you pick the parameters for these 2 logistic functions is a huge constraint. There are a dozen terms in that sum and tens of millions in this sum. Okay? Mm-hmm. You can. In fact, so we don't stop there. So we have a green view too, which has to do with HTML features on particular web pages. And that's why when we were browsing the knowledge base, there were a couple web pages like that one for T. So it turned out that Richard Wang, one of the PhD students working with William Cohen, did a whole PhD thesis on how to develop a learning algorithm that would use repeated HTML structure on web pages. And so we just incorporated the result of his PhD thesis as a third learning method. Andy Carlson was a PhD student who contributed the pink one in his thesis, and then Burr Settles was a postdoc who worked with us who contributed this one. But you're right, the more the merrier. And in fact, analytically, you can prove that for co-training, if the number of views grows, you call the number of views n, and if these different views are conditionally independent given the true label, then you can show you get an exponential improvement in the sample complexity of learning as a function of the number of these views you put in. Okay, so that's one way we can couple the training of different functions with the result that now the unlabeled data becomes a very valuable constraint on the joint choice of parameters across these different functions. Okay, so that's one, and that leads to learning these kinds of things that we looked at. But here's a different thing we can do. Nell is also not learning just one category, it's also learning multiple categories. So even if we do have different views of the input to the function, we can use those and also take advantage of the fact that there are many categories Nell is learning. So not only is it trying to predict person, but it's also trying to predict whether a noun phrase refers to an athlete or to a sport. And in the ontology, when we define a category, we define subset-superset relations. So Nell is told when we define the category athlete that that's a subset of person. And once it knows that, then we know it knows that any noun phrase for which it decides to assign the category athlete through these classifiers, it must also, to be consistent, classify those same noun phrases as people. You can't be an athlete and not be a person. And similarly, anything it decides to assign athlete, it must say is not a sport. Baseball is not an athlete, right? So here's a different way of coupling the training of these functions. And again, you can change the objective function if you think it through, so that you end up with one single big objective that you're trying to optimize as you learn the parameters of each one of these black line Boolean valued classifier functions. Yes?
Is that capable of learning these subset relations as well, or are these always related?
Is it capable of learning these or what?
Relations.
Sorry, or relations?
Relations,
Yeah.
This is a part or this is a whole of something.
Right. So the relations are actually the third thing that get added to this. If I understand your question, let me just show the next slide. So the other thing that Nell learns are relations. So for example, 2 argument relations as opposed to just 1 argument categories. So some of the classifiers Nell is learning are ones that, given one noun phrase, try to classify it into categories. The second type of thing it's learning is, given a pair of noun phrases, classify that pair yes or no, is that an instance of the relation team plays sport, or coach coaches team? And these are actually typed relations. And so the learning of those classifiers of noun phrase pairs end up coupled to the learning of the single category classifiers as well, because in the end you can't really say that yes, Bill Belichick, Pittsburgh Steelers plays the sport football, unless you also agree that Pittsburgh Steelers is a team, because that's a requirement for team play sport, and that football is a sport. So we end up coupling the relation classifiers that are being learned to the category classifiers that represent their argument types. And so when you put this all together, there are several thousand functions that Nell is learning. Each one of these black arrows represents a simple classification function. You put them all together, their training is all coupled, and now every unlabeled example, in a way you can think that this network of constraints tells you what are legal joint assignments to each of these categories and relations. There are some combinations of labelings that are consistent with the coupling constraints and others that are inconsistent. And so the training objective is really to try to become as consistent as possible over the unlabeled data, plus as correct as possible over the known labeled examples. And it's that consistency with respect to this whole network of things that makes Nell actually able to do coupled semi-supervised learning for several years and not run off the tracks the way that simple first example did. Was that getting at your notion of relation, or did you mean something else?
Actually, I didn't mean something else. So noun phrase plays this sport is one kind of relation.
Uh-huh.
I was thinking of the relation subset of, like, so athlete is a subset of person, doctor is a subset of person.
Right.
So these kind of subset relations, how can it like explicitly gather from the data that is?
Oh, that's great. Okay, so the question, a very nice question, was what about, okay, so we have relations like person, coaches, team. What about getting the system to actually explicitly read the subset relation that that noun phrase 1 is a subset of noun phrase 2, that baseball is a subset of sport, or that wolves are a subset of predators, for example, right? In fact, Burr Settles, our postdoc, had the same idea. And so he added to Nell the subset relation, and without changing the learning algorithm, just added it as another relation to be read. And Nell is now reading subset relation and has read things like wolves are a subset of predators and so are lions, and predators are a subset of animals. So this is a way in which Nell could, in principle, start growing the categories. We haven't been brave enough to let it do that because it isn't quite, we're a little worried that it reads subset inaccurately, and we are afraid of allowing that inaccuracy to get into the ontology itself. So I think what we should do is probably let it read them, and then we would human vet them. With a little bit of human effort, we could say, yes, 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 no, not that one, yes, dash, yes. And so if we let a person just approve the proposals, that would be much safer than letting them just go in. And that, to be honest, that's also what we did with the relations that I mentioned. Nell is inventing relations. It proposes them. We humans decide whether it can go ahead and add them to the ontology. Okay, so back to the main story. So you get the idea, right? The key idea in one sentence is this. If you want to make unlabeled data valuable during training, you can get a lot of leverage by coupling the training of many functions, because then every unlabeled example that you have becomes a joint constraint, becomes a constraint on the joint choice of parameters for each of these functions. Whereas in our first example, where I just had one category and we're trying to use unlabeled data to learn it, there was sort of no logical, rational way of taking advantage of that unlabeled data until we start making assumptions. And this kind of assumption is quite justified, right? People really are a superset of athletes. That's an assumption I can live with and even defend if somebody wants to argue about it. So that's key idea number one in Nell. It's been very useful. Okay, and it leads. Well, here's another touchstone for our course. We talked about the EM algorithm. And so you could ask, well, what is Nell's real algorithm? And I will tell you that it's EM-like. It's not quite EM. But in principle, suppose you wanted to use EM to implement Nell. What would that mean? Well, remember in EM, we talked about that. We have a set of random variables. And some of them we can observe and some of them we cannot. And in EM, we learn the parameters of this joint distribution and simultaneously learn estimates for those unobserved random variables. We could map that onto our problem this way by saying we have random variables which are the identity of noun phrases, what they look like PIRATES, that's a noun phrase. It's an observed value of a noun phrase. Those are observed. And then we have a lot of unobserved beliefs about the world, the knowledge base. In fact, every triple in Nell you could think of as representing a random variable, like Bill Gates founded Microsoft, could be the name of a random variable whose value is 0 or 1. Nell doesn't know in advance whether it's 0 or 1. In fact, every describable belief, including Bill Gates founded Carnegie Mellon, would be another random variable whose value is 0 or 1. You and I know it to be 0, but Nell might not. So you can think of the knowledge base as representing a vast set of potential beliefs, each one of which is a random variable with a true or false 1, 0 value. And that they depend, their truth depends on properties of the associated noun phrases, like what context are they found in, what letters are they made up of, and so forth, which are, of course, observable. So if we think of it that way, you could think of an EM thing where in the E step, you want to estimate the labels of each of these unobserved variables. Basically, you want to estimate the truth of every potential belief that could be represented in terms of our text. And then on the M step, we're going to take those current estimates of what's true and false to retrain the parameters of our classifiers that map from the observed noun phrases to our beliefs about them. Okay, and this would be very analogous to when we introduced EM, we were talking about naive Bayes, and then we could have some examples with missing labels, some with observed labels, and we would just iterate, retraining our naive Bayes classifier, and then re-estimating the correct label for them, then using those re-estimated labels to retrain naive Bayes and iterate to convergence. So we could try, in principle, something like this, but the scale doesn't work well. So Nell has roughly 25 million noun phrases it's routinely using, which means 10 to the 14th pairs of noun phrases, like Bill Gates and Microsoft, and each relation is a classifier of one of those. So it's not at a scale where we can actually execute an E-step even once. 10 to the 14th is just too many things to explicitly label. So in fact, the way I think of Nell's algorithm is, let's call it E prime M prime. On the E prime step, it does re-estimate the knowledge base. Nell is in an infinite loop, and each time it goes through the loop, it first re-estimates the knowledge base using all of the learned classifiers that it has so far. But it limits how much change it can make on each step, and that makes it tractable. Like, we only allow it to add up to 250 new noun phrases per category on any given step. So then the E step really is re-estimate the knowledge base, but with some bounds to make it tractable. We don't let it just consider every belief, just the ones in which it's most confident, for which it has the most evidence. And then on the M prime step, it uses that knowledge base to retrain each of its reading components, as though the knowledge base was, well, using that probabilistically labeled knowledge base. Okay. So it is an EM-like algorithm, but we can't really do the whole EM thing properly, partly because we can't handle 10 to the 14th different variables to label in the E step. Okay, but it's very much motivated by EM. Okay, and so that leads to a very simple architecture for Nell, which is there is a knowledge base, and there are a set of these different reading components that can contribute labels. And it's just in an infinite loop where it will take the current knowledge base and retrain these things, and then use these retrained things to propose updates to the knowledge base, which get integrated in some way that I'm not going to talk about. Okay, but that's the general architecture of the system. Okay, so let me zoom through the other 3 good ideas more quickly than this. So I think this is actually very closely tied to what we've been doing in the class. We've been talking about semi-supervised learning methods, co-training, ways of using unlabeled data. And you can see we've taken what we could from those ideas that we've discussed in the course and tried to package them at scale for Nell. And one of the nice things we found is that the more functions you force it to learn in this coupled way, the better the learning works, even with primarily unlabeled data. Okay, so the second good idea comes from this observation. If coupled learning, coupling the training of many functions, is a good idea, how can we get more coupling constraints? So good idea number 2 in Nell is learn them. So now that Nell has a knowledge base with 90 million beliefs, it can just put aside reading for a moment and have a separate learning algorithm that tries to discover empirical regularities over those 90 million beliefs that it holds. So for example, Nell has learned that you should believe with high probability that athlete X plays sport Y if you already have read that athlete X plays for team Z and team Z plays sport Y. If Mario Lemieux plays for the Pittsburgh Penguins and the Penguins play hockey, then Mario Lemieux plays hockey. Okay, this is a rule that Nell learned. It didn't read this rule. Maybe somebody wrote it down in text on the web. I don't know, but Nell certainly didn't find it. It just discovered this happens to be an empirical regularity that holds in that knowledge base of 90 million things that it has read. And so has a learning algorithm for learning these kind of rules. And those rules themselves, each one of them, become another coupling constraint for tying together predicates it's trying to learn to read, right? So if you think of that rule, it's actually another constraint, just like the one that says, if you're an athlete, you must be a person. This one's saying another logical constraint's a little bit more complex, but it's really a constraint that ties together the three relations that the rule mentions: play sport, if plays for team, and team plays sport. And so that rule is really a new blue coupling constraint among the different functions that the system's trying to learn. Okay, so now so what are we just seeing? Go back to our original goal. We want to somehow figure out how can we build a learning system that has the virtuous property that once it learns knowledge of one type, it actually helps it become a better learner of a knowledge of a different type. So here we have that. These kind of rules, which have nothing to do with reading, they just come from data mining the knowledge base, basically. But once every one of these you learn, it becomes a new coupling constraint, which will be used now to further constrain what are legal joint assignments over these different beliefs you can hold, especially when they involve these relations. And so they make the unlabeled data even more valuable constraint to retrain these black reading functions that we have. And then as those black reading functions become more accurate, they give us a better knowledge base from which we can learn more precisely correct empirical regularities. And so here's an example of a virtuous cycle where there are two types of knowledge. I'll call them the reading knowledge, all these black classifiers, and the non-reading inferential knowledge over the knowledge base. And by having the system learn both of those simultaneously on each loop, we get a really helpful synergy. So I don't have a theory for that, but I think you can see the intuition about why this would be a good idea. Yep?
So do you have a threshold that like above 0.9 only Nell will have a relation, otherwise it won't? Because
Yeah.
if we keep the threshold as low, Nell will start to learn very fast.
That's right. That's right. So, and if we put the threshold very low,
It might make mistakes, but it will learn very fast.
that's right. So there's the trade-off of speed of acquisition of beliefs and the correctness of those beliefs, and where we set a threshold on these things. So that's something that we've recognized and kind of heuristically tuned for the system. But I would say we don't yet have a good analytical grasp on that, and we don't have a way in which Nell self-reflects enough to actually choose that trade-off itself. But the trade-off you're talking about would be a good candidate for future Nell learning. Right? So I think anything that we do as developers of the system, I would like eventually to transfer to Nell to have enough self-reflection on its own that it could have a chance to do the same kind of reasoning and improvement that we do. So that's a goal, not something that we're currently doing. Okay, so I'm going to avoid the temptation to tell you a lot of details about the inference scheme. But I will tell you that Matt Gardner and Nell are two PhD students, both of whom have been, Nell graduated now and did his thesis developing a more fancy kind of rule learning for Nell. And Matt Gardner is making it even more interesting. There's a whole story underneath there, but for now I'm just going to leave it as Nell's learning these rules, and it's very helpful. And I'm skipping over a bunch of slides. Okay, to get to key idea number 3. So key idea number 3, I already mentioned that Nell is inventing new relations that we didn't put in by hand to the ontology of the knowledge base. How is it doing that? And this is an algorithm due to one of the students who took a class I taught and got interested in this, Tahir Mohammed, and Stefan Hrushka, the professor in Brazil. And they were interested in how can Nell escape the chains of the ontology that we've manually given it. So in that ontology, there are roughly 1,000 predicates at the moment. You know, things from beverage to athlete to emotion to plant to landscape feature to all kinds of categories and all kinds of relations. But it's still very small compared to all the things you can actually talk about in natural language. So one of the things Nell is going to have to do, if it's going to keep getting better and not just plateau and stop learning, it's going to have to expand its representation. So Tahir and Stefan were interested in this, and they came up with the following algorithm. They said, well, our goal is to add new two-argument relations to the ontology. So the algorithm is for each pair of categories, for example, C1 might be person and C2 might be musical instrument. Find all the pairs of known instances of person and musical instrument, and then cluster them in terms of the text contexts that connect them. And it turns out when you do this, now that Nell has a knowledge base and it has plenty of noun phrases that it believes do refer to musical instrument and plenty of noun phrases it believes do refer to musicians, then it finds that sitar and George Harrison co-occur in sentences way too frequently to be coincidence. And so do tenor sax and Stan Getz. And furthermore, the text between those two arguments in the sentences is very similar. You'll see sitar master George Harrison, and you'll also see tenor sax master Stan Getz. And similarly, these other text things too. So here you have, through this clustering process, it's not that complicated, very strong evidence that there's some kind of phrasing that people are frequently using to relate these anomalously frequent pairs of noun phrases. And so this algorithm takes that as evidence that there's some kind of relation between musical instruments and musicians that people are talking about that's not yet in Nell's ontology. And so it proposes adding a new relation. It gives it a name master simply because that's the phrase that's closest to the centroid of the cluster that it gets. And in fact, it'll make it a typed relation by calling it music instrument master musician. And then it'll make up an inverse of that called inverse of music instrument master musician, which explains those horrible relations you were seeing when we were browsing. Okay, but that's what it does. And so when it looks at the pair cell type in chemicals, it finds epithelial cells, which it believes already is in the category of cell type, occurs a lot with surfactant, which it believes already is a chemical. And it proposes cell types that release chemicals as a relation. Now, some of these things that it proposes are good. Some you look at and they're a little wacko. But for example, it also proposed that animals live in cities. And the examples I had were tigers live in Detroit, rams live in Los Angeles. Help me here. Somebody who knows more professional sports teams than I do can come up with some other examples. But the Detroit Tigers is a team, and the Los Angeles Rams is a team. But it found rams in Los Angeles occurring a lot together and tigers in Detroit, and so it proposed that animal lives in city and gave those examples. So that was one where the human vetting came in and said, no, do not add this to the ontology. So it's not a perfect algorithm, but it does propose a lot of very useful relations. Here are some of them that we have allowed in. And you saw others when we were browsing T. But like food that decreases the risk of disease, clothing goes with clothing. Nell is now making fashion recommendations. Believes t-shirts go with jeans. Country has sports fans. Baked goods served with beverages. Okay. So this, again, is a complementary kind of learning process that coexists with the training of the reading classifiers and the learning of the inference rules that then infer beliefs from other beliefs rather than from reading. And then in parallel with that is this process that's trying to generate, based on the reading competence developed so far, trying to generate evidence for the existence of new relations, which then are adopted into the ontology. And you had asked the question before about reading the subset relation. I think of that as another way of extending the ontology. And so this is the work of Burr-Settles, which was to train Nell to just read the subset of a relation. So he actually, without changing any of the learning code, Burr just added the relation subset of and gave a dozen examples and had Nell try to learn subset. It almost worked, but it wasn't particularly accurate in its learning of subset, and so we engineered it in the following way. We picked some categories and had it learn subset just within the categories. So in the end, he introduced it a relation called animal is subset of animal, and he just gave examples of that. And it turns out there's a lot more consistent text patterns to be learned if you restrict to a type like animal. Or foods. Food is a subset of food. And so, in fact, Nell is now learning to read many different typed subset relations. But the results are pretty nice. So for reading argument 1 is the subset of argument 2, and both of them are types animal. Nell used to have a leaf node called animal, and all of these black things were members, and so were the red things. But now it has read that hamsters are a subset of pets, and ferrets are a subset of pets, and pets are a subset of animals. So effectively, the red thing is what it discovered by reading the subset relation. And here are some of the patterns that it's learned to use to read the subset relation. So it's like hamsters and other medium-sized pets, or snakes and other jungle predators, or lions and other magnificent predators. So these are the kinds of reading phrases that it has discovered refer to animals being subsets of animals. And similarly, I could show you the example for chemicals. It learns a separate relation subset, but where the types are restricted to be chemicals. And now it learns like natural gas and other hydrocarbon fossil fuels. And fossil fuels comes out as an intermediate category in the hierarchy underneath chemicals. So this seems to be a helpful mechanism for proposing additional subcategories. This one is currently at the state where it looks promising, and we should incorporate it into the 24-hour-a-day run of Nell. So the way I think of the research project is we have this real software system that's running 24 hours a day, and then we have a whole bunch of research going on around the periphery of that. And whenever a research project succeeds so much that we trust it, then we actually put it into the 24-hour-a-day run. And this one is still on the periphery. Well, it's actually reading these things, and if you browse the knowledge base, you'll see this relation, animal subset, but you won't see that it's actually now a category that Nell is treating in its other ways as a category. We'll probably insert this one. I saw a hand question. Yes?
Some of the reading patterns are given by the trainers, or are they learned from
What's given by the trainers?
the reading pattern?
Oh, the reading pattern. No. So these were learned. What's given by the trainer is, as usual, a dozen examples of subset. So we might give, like a training example, we might say, water is a liquid. That could be a training example for chemical subset. And then given a dozen examples like that, Nell learns these the same way it learns that tea grows in landscape features like valleys. It learns these extraction patterns. And then it uses those to find more beliefs like these. So the training examples are pairs of noun phrases that satisfy the relation. Yes?
So all the categories are given?
Yes, all the categories are given, and initially relations are given. We now have a mechanism for generating new relations as we go. And this is a candidate for generating new categories. But I think we need more work, more research on how to continuously grow the ontology. So these are our current best mechanisms. But I think better things could be done. Yes?
You mentioned earlier that like a thumbs up and thumbs down thing. How does that tie into the algorithm? I mean, is it simply just a majority thing?
So it's a little complicated, but to first order, people can propose thumbs up or thumbs down, saying something is true or false. Nell takes that into consideration, but it doesn't treat it as perfect knowledge. So so we'll use that contributed thing as a training example, but it won't necessarily believe it with 100% accuracy in its knowledge base. It'll just use it as one of many training examples that it's using to retrain its readers. And so if you lie to Nell, it won't hurt it too much, unless you sort of get a huge gang of people to jointly lie, then you can hurt it. But so it treats people's advice as useful, but not a hard constraint on something it must believe. Yeah?
Is there a weightage that you give to different types of web pages? Like research journals have more weightage than blog posts. Like text taken out from research journals or scientific papers is much more.
Oh, I see.
Than blog posts.
Yeah, that's good. So the question had to do with, what about weighting different documents, different sources with different credibility? We're not doing that. I think there's a big opportunity there. And PageRank, for example, is an algorithm for assigning credibility to web pages based on how many others point to it. I think if we use something comparable to that, it would probably be helpful. Right now, well, we're not doing that. It's a good idea. I don't think I'd put it in the list of top 5 most dramatic shortcomings of Nell. I mean, I think I would put in the top 5 dealing with time. Time is a severe problem for Nell. It's really hard to learn to read about time. I would also put in the top 5 that Nell is now starting to saturate some of the things it's trying to learn. So, for example, if you browse the knowledge base, you'll see that it pretty much has all the countries. There aren't any more countries. So, over time, its learning of countries kind of looks like this, and then it kind of flattens out. Fortunately, flattens out. Actually, it went a little too far. It has some non-countries in there, too. But the thing is, it's not growing. And similarly, it has pretty much all the colors it's going to get. The most recent colors that it's added are very obscure colors like, you know, sea turtle green, and things like that. So one of the shortcomings is starting to saturate many of the things that it's been reading about. And the only way out of that I can see is to have more aggressive mechanisms for extending the ontology automatically so that it can keep hatching new learning problems. It's also currently not a very good reader of single sentences, like the one I just spoke. Now it has very little competence to understand a 23-word sentence, which is the first sentence of a New York Times article. So we're doing a lot of research now on trying to develop learning algorithms that will take the background knowledge Nell has and use it to guide the training of single sentence, deep analyzing readers. Yeah?
Is there a like mechanism to freeze an area of learning that you have learned, like you're done with this and you shouldn't learn any more in this area? So like,
Yeah.
sun is at the center of solar system. Nell shouldn't, you know, change the weight again and again. So it should freeze that and move on to next thing. Is it possible?
Not really. We don't have that. We have, just as kind of a convenience for the software engineering, we can turn on and off learning of an entire predicate, category, or relation. But I'm not sure how I feel about your proposal. I'm not sure I want my learning system to decide forevermore I'm not going to question this belief. I think I'd just as soon have it continually question it, maybe routinely say, oh yeah, I still believe the sun is the middle of the solar system. But, you know, if Copernicus had worked that way, where would we be today? So, let me show you the final slide and we can take some more questions. You see, I could talk about this for hours. So I just want to put this slide up. So these were the 4 key ideas. We talked about 3 of them, but the 4th one is just do what we did, that is have Nell learn different things in a sequence. Like first, it was just learning to classify noun phrases and then relations. But after it did that well enough, it could start learning those inference rules in the knowledge base and inventing new relations. But it couldn't do that at the beginning because it didn't even have instances of musician and musical instrument to look for the relations. So there's a kind of curriculum that effectively has guided the development of Nell. And I just wanted to put up this list because there are a whole bunch of fun things going on. We are working on self-reflection. We are working on integrating this with a system that Professor Abhinav Gupta has, which he calls his never-ending image learner, which is trying to do for images what Nell is trying to do for noun phrases. And now Neil and Nell are communicating and trying to co-teach each other. We are doing what we call micro-reading, trying to work on individual sentence processing. In fact, Abu's research fits into this category, and some other things too. So we probably should officially end because the next class begins in 5 minutes. Thanks, but I'll hang around for other questions.
So are you also